Ladies and gentlemen, our honored audience, good afternoon for you in Europe, good evening for you in Indonesia. Welcome to our second webinar, brought to you by ISPEX NL, Institution for Science and Technology Studies in Netherlands, and PPIE, an Indonesian Student Association in Enschede, Netherlands. My name is Mutia. I'm a PhD candidate of Chemical Engineering at the University of Twente. Today, I'll be your host in this webinar. This webinar is live broadcasted from the city of Enschede in the eastern side of Netherlands. And today, we have a special speaker, Dr. Cheryl Raditya, who is an expert in the field of chemical engineering, especially in organic membranes. Before she gives a talk to us, I would like to share and introduce herself a bit. Dr. Cheryl Raditya was born in Surabaya on the 3rd of December 1984. In 2006, she obtained her Bachelor of Science from Institute Technology Bandung from the field of chemical engineering. Afterward, she started working as a CEO at the Flowtech Water Management Company in Indonesia. Then she obtained her master's degree in the Department of Civil and Environmental Engineering at the Stanford University in California, USA, and the Civil Department of Nanyang Technology University in Singapore. In 2011, Cheryl started her PhD research as an Erasmus Mundus awardee. And in November 2015, she received 3 PhD degrees from 3 different universities in the field of chemical engineering, from the University of Twente in Netherlands, the University of Leuven in Belgium, and the University of Montpellier in France. During her studies, she was active writing many papers and to be published in international journals. Her latest publications were published in the Journal of Membrane Science, entitled Solvent Permeability Behavior of PDMS Grafted Gamma-Alumina Membranes. And today, she'd like to give a talk about organically-modified ceramic membranes for organic solvent nanofiltration. So, Cheryl, you have 30 minutes to present your talk, and floor is yours.
As already introduced by the host, I'm Cheryl, and today I'm going to give you a talk regarding the organically modified ceramic membranes for solvent nanofiltration. So this work has been performed in 3 different universities, in the University of Twente, in Leuven, Belgium, and also in Montpellier, France. In each university, different topics were studied. So first, we graft the Mesoporous gamma-alumina membranes with PDMS, and it's done in the first place. And then we investigate the solvent formation and rejection behavior of PDMS grafted gamma-alumina membranes in Belgium. And then in France, we graft PG to the gamma-alumina membranes. So first, I'm going to talk about what is nanofiltration. Nanofiltration is a separation technology, and it has become important in the recent decades because it consumes less energy as compared to usual separation process such as evaporation and distillation. We can use nanofiltration to recover organic solvents. Like if the industry use a lot of organic solvents like in ton, then we can again use the clean solvents using nanofiltrations. And then it's also used for solvent recycling or recycling of high-value product in food, biodiesel, pharmaceutical, chemical, and petrochemical industries. So filters that we know in our daily use, it has different pore holes from the biggest size, like the picture on the left, until the smallest size, like in the coffee filters. Even we have currently filters that you cannot see the holes anymore. So it's really you need a microscope to see the holes. And in industries, we use that a lot. And how does a filter work? It's a very simple principle. So first you have a membranes, and then the membranes must have pores or holes. And then you apply pressure, and then the direction of the flow will be like this. And then you see these dots, it's a solutes, we call it. something that you want to filter, and then it works by size exclusion. So then here you see that the solutes with size almost similar to pores or holes, or even smaller, it can pass through, while the bigger size, it was retained. So this is just the principle of the filters. And it also works for nanofiltration. So nanofiltration, the pore holes is very small. It's around 0.5 to 2 nanometers. And in this work, I have ceramic membranes. You can see the picture here. The pore size is about 5 nanometers. So we need smaller pores than that because it's still 2 times of this. And that's why we do organic grafting. So on the right is the picture of the gamma alumina membranes. So the ceramic membranes that you see before is just like a white coin, but now you zoom it using a electron microscope, and you can see from here there is a small holes, and then it grows bigger and bigger. So the one that has small holes like this is gamma alumina membranes, and it's 3 micrometer thick, and it has a pore size, pore diameter of 5 nanometer. So we want to reduce it to 2 nanometers, and that's why we put organic molecules in here. And it's only towards the gamma alumina because the below part is not reactive for organic graftings. And the nice thing about material science is that you can combine its chemical molecules. You can arrange it so that you can have the properties as you want. In this case, as an example, we want hydrophobic pores. So it means water resistant. And you might also heard hydrophilic phrase often. It means it's suitable for water or alcohol. So that's we call it polar solvent. So then you can use chemical molecules that is suitable to your purpose. That is really important. The normal ceramic membranes, it usually use 3 different layers. In this picture, we only have 2 different layers. Usually to have a nanofiltration ceramic membranes, you need a very small, again, ceramic membranes on top of this, with a pore size about 1 nanometer. But with organic grafting, you don't have to use that layer. You just put organic molecules in here. So it's very simple. You just need ceramic membranes. It's metal oxides, alumina, silica, or titania. And then you have reactive sites here. In this case, we have a natural presence of hydroxyl groups. So we can react this one with the suitable functional groups, and then you can anchor a polymeric chain on top of the substrate. In this case, I use silanol. So this is silanol, and then after hydrolysis, you can have a covalent bond SEO with the metal oxides. There are a lot of different routes. You can find it in the literature other than silanol, so like phosphate or something like that. And it's really depend on you what methods you want to choose. But in the literature, this is the most common one so far. So in this case, I choose PDMS. Why? Because it's really hydrophobic, and we want to make a water-resistant membranes for solvents like toluene, hexane, or something like that. And then, so this is the silanols, and then this is the PDMS. You just connect it using chemical reactions. I use toluene as a solvent, and then we do reflux for 24 hours. And then you test whether it's really grafted, whether you have a covalent bond here, and you did it by FTIR, and you see in the 1000 region, you need to have something like this. Okay, and then we also compare it with the FTIR of original gamma alumina without modification and after modification. And then you see the terminally anchored polymers. It gives the surface characteristics That is, it becomes hydrophobic after grafting, while before it was hydrophilic. And then the permeability reduced. Why? Because there is now already organic molecules in the pores. So the pore is now smaller, so the toluene that can pass is very small. And then we check also with the boiling test whether the in toluene, hexane, and isopropanol, and if you see no changes in the FTIR spectra, that we assume that to be stable. So this is the possible structures of pores. For example, this is a pore and this is the organic molecules. So you have something now inside the pores that can reduce the holes. So the liquid can only permeate less because there is already a presence of organic molecules. Using SEM EDX, you can see the picture of the membrane. So this is the gamma alumina, and this is the alpha alumina. As I already said before, we put organic molecules in this layer. So in this layer, using PDMS, it has a SE, and using this, you can see there are a lot of blue dots representing the presence of Si molecules. So you see it drops quite homogeneously throughout the entire layer of gamma alumina. And then to make the pore even smaller, we can again link this one. So this one, we link it using cross-linking so that it becomes a net. Looks like a grafted network, and we can use that using cross-linking agent. You see that it has 4 functional groups in its sides. You can even use a cubical molecules. It has even more, like 8, 12, or 20 functional groups. It's even make it more rigid. So the possible structures resulted, it can make network horizontally and also vertically. And we see through rejection tests, so we pass feed, and then we see, okay, it gives 95 rejection, means that 95 of solutes would not pass through. It means it can retain better. So to make the pores hydrophilic, instead of grafting PDMS, we graft with PEG. We test different kinds of grafting agents. This is all PEG, but the difference is that in the first part, we just random grafting takes place, while in the second one, by making use the hydrogen bonding of uridyl groups, like this, you can make a self-assembling grafting. So it will first self-assembly by itself, and then it graft with membranes. To know how many of PEG was grafted, we can use Thermo-Gravimetric analysis. So we actually put as high temperature as possible, every minute, like 10 degrees, and then you see at 700 degrees there are some masses left, and this is the gamma alumina because it doesn't burn out even at 1200 degrees Celsius. And then the amount that is burned out, we assume it to be organic matters. When you know the MR of the organic matters, then you can calculate how approximately the moles of the organic matters that are there in the sample, and then this divided by the amount of gamma alumina, you can get grafting. So in here we have like a 1 grafted PEG per nanometer square for grafting agent D, which is using this agent, and that we try to graft it to the membranes. So after we graft it to the membranes, we check again whether the grafting has occurred, and the presence of this smooth peak shows that the covalent bond of SeO metal oxide has been formed. And then we see that the contact angle also changes after grafting, that it becomes 40 degrees after grafting. And then Again, the flux is reduced because of the presence of Eg in the pores, and also the rejection. We test it also for different solvents, and it gives different rejections with regard to the membrane performance. So, as we know, the solvent nanofiltration, it uses various kinds of solvents. There are various kinds of solvents in the industries that you want to filter. So it's really important if you can predict the membrane performance by simulation or something like that. And to do that, you need to know what is the important parameters that affect the membrane performances. To do this, first you can try different transport models that are there in the literature, and you can see whether it fits. From there, you can identify if it fits or if it not fits. What is the possible infection mechanism you think about the membrane between the membrane and solvent? And then you can then propose a transport model to describe the solvent transport to the membranes. So first, you want to know the effect of the applied pressure, because usually when the pressure is higher, then you have a higher flux. Means there are more solvents pass through the membranes. And you see for each solvent, it doesn't give the same flow. Different flow rates was found for each solvent, and it develops linearly with the applied pressure. So we have two types of PDMS grafted membranes. First, it's grafted with the N of 10, and the other one with N of 39. And for both membranes, we see a linear relationship. This is very important because if the flow is higher, much higher when the applied pressure is higher, then it means you have something like a burst of membranes. And if you have very less, it means that you have compaction. Means that you cannot pass any solvent at high pressure. So it's already known that the pore flow model, we call it usually Hagen-Poiseuille law, and this is it says that the membrane flow proportionally related to the applied pressure and the solvent viscosity. Only that, so only the pressure and only solvent viscosity will influence the flow rates. However, in the law, the K is constant. But here, if we try using different solvents, we see different K. So it's not according to the law. And that's why we modify this equation so that we can model the transport behavior of grafted membranes. That is by making the K as a function of S. What is S? So you see here, the ceramic part is actually rigid. So you only have a pore flow here, and then only the pressure and also the solvent viscosity influence the flow rate. But now we have our organic molecules, and it can go up or go down according to the interaction with the solvent. We know that organic molecules, it swells differently in different solvents. So if like dissolves like, it swells. If it doesn't like the solvent, it will collapse. What is the implications? The pore size of this one, although these two are two similar membranes, two exactly similar membranes, if you use solvent A, it becomes smaller. If you use solvent B, it becomes greater. So it means that if you filter something, this one won't filter really well. Well, this one will filter well. So the same membrane can give two different behavior if you use different solvents. This knowledge is very important when you use this same membrane for different solvents in the industries, because you can have different performances although you use the same membrane. So for that, we know from the experiment that the solvent permeation is influenced by the solvent viscosity and the swelling degree of the grafted polymer. And then that's why the K that is in the Hagen-Poiseuille law, we modified it and we input absorption parameter. So this is the parameter for the interaction with the membrane and the solvent. And the way we do this equation is that when the sorption is high, the membrane pore diameter becomes smaller. When the sorption is low, the membrane permeation becomes greater, and that's why you have a negative here. Okay. So the conclusion is that we have presented the grafting method of PDMS, DMS network, and PEG2 gamma alumina membranes, and the solvent viscosity and solvent sorption is important in influencing the membrane performances in different solvents. The important outlook of this is that there are so many interesting molecules that can be grafted, depends on the purpose of the membranes. So if you want to make membranes for metal removal or for enzymatic reactions, then you can graft molecules that you want, that you know that will give the result as you want it, and you can graft it. So you don't have to always graft PDMS of PEG. It's the options is your choice, and it's free to graft anything that you want as long as you have a suitable chemical route for it. And then the membrane performances can be different depending on the interaction between the membrane, solvent, and solutes. So when you want to make a membrane, then you can consider what is the interaction with the solute that I want to filter and with the solvent that I want to use. Then you can tailor the membrane and make a strategy to make a good membrane for that special applications. So this is the end of the presentation, and I would like to acknowledge the people and the groups that have been working together for this project. It's from the European Commission, where funding the Erasmus grant, and then the Mesoporous of the University of Twente, the Institute European des Membres in Montpellier, and also the KU Leuven, Belgium. Thank you for your attention.
Okay, Dr. Cheryl, thank you for your talk. There's an interesting presentation that you've given to us. So after watching Dr. Cheryl's presentation, I'm quite sure that now you have some questions and comments. So now please put your comments and question on our website, ispex.nl/webinar/webinar002. So we're now waiting for your question and comments. In the meantime of waiting your question and comments on our channel, now I already have at least 3 questions from the audience. I think the first one from the bachelor student in Indonesia. Dr. Cheryl, could you please a little bit tell us about the difference between organic and inorganic membranes, because you already present about ceramic membranes as a type of inorganic membrane, right? Mm-hmm. So now the audience would like to know about the difference between these two.
Okay, that's an interesting question. So the difference between inorganic membranes and organic membranes is that if you say organic membranes, it's normally made from polymer. So it has CHON in the membranes, while for metal oxides membrane or inorganic membranes, it usually means metal oxides membrane. So it used inorganic molecules like Si, Ti, Al in the membrane, and it's like a connect with O, so ALO, ALO. Yeah. That's the different. And do you also want to ask the different about the properties? Sure.
Yeah, you can also explain.
Okay, so the polymeric membranes is like a plastic membranes that you often see. So it's cheaper normally, while ceramic membranes is really like a ceramic that you use for glass and for mugs when you brush your teeth. And before glazing, the ceramic is actually porous. So if you put water in ceramic glass, the water actually can go through the pores in the ceramics, but the glass that we use now, it has been glazed with a layer, and that's why it's not permeable anymore for water. And it's really what we use in the industry also. So it has a ceramic tubes very big, and usually it's used for high temperatures. So if you want to do separations at 300, 200, or 400 temperatures, then you usually use, 400 degrees Celsius, then you usually use ceramic membranes.
Okay, so it depends on the purpose of using, right?
Yes.
Okay. This also related to the second question. Because you already talked about nanofiltration. In what case the nanofiltration will be the most prospective tool for separation? In what case? I mean, for waste industry or something else?
Oh, in which case?
In which case? Yeah.
Grafting membranes can be used, or only ceramic membranes?
Only ceramic membranes.
Okay. Yeah, as I said before, it's used for example, recycle of catalysts. It usually needs a high temperature. If you use polymeric membrane, it will swell. You can see if it swell, if it looks like melting, but it's not. So the pores becomes bigger, and you cannot filter using that membranes anymore unless you process or something like that. So you usually put ceramic membranes because it's stable in diameter, it's chemically stable in high temperatures.
Okay. Okay, good answer. Interesting. So the third question is, in what purpose do we need to use linking agent on the ceramic membranes?
Okay. So the cross-linking agent is usually useful if you want to make something rigid or more robust. So it depends. If you want to make a very smaller pores, I think it's good if you do cross-linking. However, don't forget that if you use cross-linking agent, then the flow becomes smaller also.
Okay.
So
could you please a little bit show us how about that? Yeah.
So you see the picture on the right, on the bottom right of the page. You see the red represents the cross-linking agent. So using that, you will connect even this one and make a network. So that's why the flux becomes smaller, because then you have smaller pores. Yeah.
Okay.
You can also use cross-linking agent if you want to modify polymeric membranes. So different than my presentation, it's for organic membranes. You can prevent the polymeric membranes from melting, or we call it swelling. So you can maintain still the rejection properties at slightly higher temperatures than normal.
Okay. Okay, now I received new question, also from Indonesia. Maybe he is interested in looking for your outlook, because previously you mentioned that in the first point, yeah, in the first point, sorry, I'm waiting. Okay. In the first point, you mentioned that there are many interesting molecules that can be grafted. Depends on the purpose on the membranes. What do you think the most prospective molecules other than we already discussed in the presentation? For the future, maybe you can make a recommendation for the future research.
That's a very good question. What is currently being done is actually you can also graft complexing agents. So if you want to remove metals, this complex can catch the metal ions, and you can therefore graft something with complex. And also you can also graft enzymes, so that if you want to use it for food applications, then you can also do it through this enzymatic membranes.
Okay, interesting. Because now I also have a question for you. What do you think about the application of this research for the future? I mean, for the industrial application, is this ready to be applied in industry, or still need to be developed for the research?
So thank you for the questions. Actually, so the ceramic membranes is already commercial in the market, but then you only have limited pore size availability. So you don't have all types of pore sizes, and if you use polymers and if you graph organic molecules, you can better tailor the pore size as you want. So you can choose the chemical molecules, and then you can have the pore size as you want. And regarding whether it can be applied now in the industries, it's really a complicated, I mean, a long process, because then you need to select the module in where you want to put the membranes, and then you need to see which pressure is the best for the membrane. You need to see the stability in months, in years, and whether it's reliable for long-term performance. And then you can so it's still a lot of development, but of course, if like for example the user see this membrane and he or she feels that the rejection is already suitable, then it can be directly used. Okay. If they already have a sufficient suitable module and also process control for that.
Okay, has it been applied in industrial application for now? Maybe in Netherlands, in Belgium, or in France?
Okay. So the ceramic and polymeric membranes, it has been used commercially in the industry now, but this grafted membranes, it's a new process, and they still want to explore which organic molecules can be grafted and whether it's really promising for a commercial application.
Yeah. Okay, very nice. I think now we are still waiting for the other questions from the audience. Okay, in the meantime of waiting, because I already mentioned that you gained 3 PhD degrees from 3 different universities just during 3.5 years. Maybe you can also share with us what your experience working at 3 different universities in Europe.
Okay. What really impressed me during this project is that cooperation can really give a faster solution, because in each universities they have different expertise. So you go to one university, they know something about this, but they may not know something about B. So they know A, but they don't know B. Okay. So if you have a collaboration between universities, you can combine the strong point of University A, University B, and University C. So the bottleneck that you have in A can be solved with the bottleneck in B. And so that's really important to often discuss and talk about what you are doing with other people, because
yeah, because this is very interesting, because you obtain 3 PhD degrees at the same time. You are very young and very talented, and yeah, that's also the part of Erasmus Mundus program, right?
Yes.
Yeah. Interesting. Okay, I think we already come to the end of this webinar session, and before I close this session, I would like to tell you, if you miss the whole version of this webinar, you can go through the link as mentioned on our publication. You can go to istex.nl/webinar/webinar 002 to watch the full version of this webinar. And for you, the researchers and the students who are residing in Netherlands, who put the interest to share the thoughts about the research or your work, please visit our website, www.istex.nl. And you can also contact us via email to share your work or thoughts then we can visit you to your city. And that's all for this session. Thank you for watching our webinar. Thank you, Dr. Cheryl, for your time. Okay, see you in the next webinar. Goodbye.